Okay, so from last time, I promised that I was going to give a quick intro to Insight Maker before we start today, because I didn't get a chance to do that last time. So if you don't like VinSim, or VinSim isn't working on your computer for some reason, there's a web-based version of a similar program called Insight Maker. You go to insightmaker.com, and it's linked on the Canvas site. You can create a free account. And then from within Insight Maker, you can create new insight upside here to draw your stock and flow diagrams. I don't recommend Insight Maker for drawing causal loop diagrams, because it just requires you to do a lot more annotating on your own than VinSim does, but it's a halfway decent stock and flow diagram tool and just general simulation tool. So if you create a new insight, instead of giving you a blank canvas, it gives you this tutorial, which you can always go through. But once you're more familiar with it, and you can just clear that, and it gives you a blank canvas just like VinSim. And if I want to draw stocks and flows on, it works very similar to VinSim, but I'm just going to show you a couple of the minor differences here. So there's this add primitive up in the corner, and you can see things like add stock, add variable, add converter. So the things that I've generically been calling converters, Insight Maker calls variables. And converters are a special type of variable. So that's one difference, and we'll cover that, I think, after the midterm, as to what converters are in Insight Maker. So for now, you can just think of variables as another name for the generic converters we've been talking about. If I add a stock, it looks just like VinSim. It creates this new stock, and I can make that bigger or smaller as I'd like. And I can edit properties of it directly in the diagram, or down here on the side. It's got this panel down here that allows you to adjust a lot of things on it that we'll go throughout the semester. We'll sort of start drilling down into these, but for now, that's how you just pull a stock on. Now, to get flows on, it looks a little bit different than VinSim. I go to add primitive again, and I can then add, if I click on this, notice here it says flows, transitions, or links. So I need to select whether I want to draw a flow or a link. And so if I select flows, then I go down onto something that has one of these handles in the middle, this little arrow here, and I click on that, and it will start drawing a flow out if I click and hold. But it draws the flow in the wrong direction if I want an inflow. And so I'd always, by default, draws them out. And so after I do that, when it's selected, I go up here, and I can then say reverse, and then it turns it into an inflow. So that's how you get flows drawn inside here. So if I wanted the outflow, I could go and do the same thing, and I get an outflow. And so now I've got inflows and outflows, and I can name them. So I can, like before, I named this thing birth rate, and this one I named maybe death rate. And now I just need to add links. And to do that in Insight Maker, I select links, and then I do a similar sort of thing where I can drag from one to the other. And you can't really see it, but it created a link that happens to be right on top of this flow, but there's a tiny little line there. To pull it up so that it's got some curvature to it, I hold down Shift and I hit click once. And if I let go of Shift, then there's a little blue handle that I can pull up, and then it draws that link in there. And all this is in the video tutorial that I have on Canvas. I'm just giving you a sort of the nickel tour of the video tutorial. So that gives me my inflow and my link. I also need the link to the outflow. So I'll do that again with drawing a link to the death rate. Click Shift to give me the little handle in the middle. Drag the handle up, make sure I'm not holding down Shift when I do that. And this looks just like what I got in VinSim. Now to get the formulas in there, if I mouse over any of these, I notice there's a little equality, or a little equal sign up in the corner here, and there's also going to be one on the flows. So if I click on that, it brings up Insight Maker's version of the equation editor. So for stocks, I only put an initial condition, so I'll say I initially have 1 bacteria, and then I can hit apply, and then over here on the flows, I go find its one, and it then has a bunch of references down here. And so anything that I've drawn in as a link will show up under references, and then all the rest of these are just shortcuts to math functions that might be useful to use. So there's like mathematical functions down here, rounding, cosine, sine, etc. So it gives you a little bit of help in building your formulas. And so here I can say I want my birth rate to be bacteria divided by 0.75, because I said that 0.75 is my average time to reproduction. And I can hit apply there. And then on the outflow, same sort of deal. I can say, well, I want it to be bacteria maybe divided by 3. So same sort of thing I did inside Vinsim. So allows us to do all this stuff. Now, how do I simulate in here? Well, there's a simulate up here, but there's one thing that I haven't touched on yet is the DT value, the time step value. So before I simulate, I have to go over to this settings, and this looks just like Vinsim settings. Simulation start, simulation end, time units, time step. So this is your DT. These are everything else. So I can say, well, I want this to go from 0 to 5 in units of seconds, and I want to have a time step of whatever, 0.01. If I hit apply there and then hit simulate, then it will pop up a simulation that it runs in some fraction of normal speed. So it's kind of dramatic here because you're actually seeing it run. But to me, that's annoying. So I just scale this up here so that I can just see the plot. And this is showing me, I'd say, well, what's it showing? Well, the default display, if I go up and I hit configure under default display, it shows me that the default display shows me a plot of bacteria. If I have multiple variables that I would like to plot here, I can put them in here. So I can say under data, I don't only want to see bacteria, I want to see the birth rate and the death rate as well. So if I hit apply, then now I see all 3 of them show up here. And it's said, man, it would be nice to have a legend. Well, under configure, you have those options. So I can go down here and I can, under chart settings, I should be able to create that legend. So down here somewhere, and for some reason on mine, it's not allowing me to scroll, but if I could scroll down here, and hopefully on yours you can, I don't know why on mine it's not, there's options for editing the legend, and you can then, so like legend position right there. Let me try if I change that to automatic and hit apply. Then now I've got a legend, and it shows me that bacteria are the green one, birth rate is the blue, and death rate is the red. And so it's got this all plotted on here. So now you might like that plot, but unfortunately the easiest, well, I'd say the simplest way to get the plot out from here is to take a screen grab. And so what I'd like to do, what I like to encourage people to do instead of that, is you can say, well, I want to create a different plot. So I'm going to call this, well, I don't know, I can just call it new display for now. But I'm going to have it be a table instead of a time series. And so if I click on table, and then I can select what data I want out, like bacteria, then it will show me all of my time, the same thing I would get in Excel. All my times, 0, 0.1, 0.02, 0.03, every DT, and then every bacteria. And if I had multiple data, I would show them down here. And then I can just click download, and then I can bring that into Excel and plot it in Excel and do anything that I want with my Excel plotting tools. So I go into more detail in the tutorial online. I don't want to spend too much time today going over that. We'll see more Insight Maker as we move on. But I at least wanted to cover things like weird things like how you draw flows and flip them to make them inflows, and to show that you can simulate in the same sort of way and either get those graphs out or the data out that you can graph yourself, just like in Vinsim. But then the nice thing about this is it's all saved to the cloud. So if you did work here in class, you don't have to worry about where I'm saving it or anything like that. If you went home, it would open up in a web browser and you'd be able to edit it there. So that's Insight Maker. It's a very powerful tool. It's modeled after Stella, which is a pretty expensive, pretty full-featured system dynamics modeling tool. Any quick questions about Insight Maker before we move on to the chapter? And you can use either one of these for that assignment due on Sunday where you're simulating the toilet. So, yeah.
How do you do the inflow again?
Good question. So if I want to do that inflow, if I were to, let's say if I can delete this one, for example. So I just, by the way, that was a right click and it gave me all these options. So if I right click down here, then there's all sorts of things that I can edit here about font, and I can add in different images and things like that, change sizes. I am going to delete. And that left the link in there, so I'm going to delete it. So if I want to create the inflow, I go up here and I say that I am in flow mode. So that's the first thing, flows, transitions. And then the thing that I want the flow to terminate on, I click on and drag out. And when I drag it out, by default, it's going to draw the flow as an outflow. And so what I want to do then is, with that flow selected, so if I were to unselect it, I need to go back and select it so it's highlighted, and then flip it so that it goes back in. So that's the kind of trick there with that. And if you go to the settings with the equal sign here, there's this checkbox, restrict this flow to positive rates. If I uncheck that, I mentioned this briefly last time, that sometimes you see flows with two arrows, one going one way and the other going the other. And that's when I uncheck the restrict this flow. That basically means I've now created a flow that if this turns up to be a negative number, it will suck things out of the bacteria, even though you might think of it as an inflow. And so the little white dot in the middle of the triangle is the negative direction, and the filled triangle is the positive direction. And so this is arguably, a lot of modelers will say this is the safer way to do it, because a lot of times you don't want the simulation tool deciding when to sort of respect your equations and when not, because you might not want your equations to go negative, and it's basically preventing them from going negative, maybe hiding an error in your logic. So a lot of real formal modelers will say you always get rid of that checkbox so that these are always bidirectional. That way it'll help expose bugs in your logic. But the downside is it makes the diagram look a lot uglier, because now you got these two, these both directions, and it's a little harder to parse. But that's what I meant by that double arrow that I mentioned briefly last time. So any other questions about Insight Maker? Yeah.
Can you show how to do a link again?
Yeah, the links, you just go up, you have to go back in link mode. You highlight that thing, make sure in link mode, and then just like flows, you drag from one point to the next. And now I can't see where the link is because it's right on top. So I have to hold down Shift and then click once on the link, and then let go of Shift. And then with Shift being let go, I should see that a new blue dot showed up, and that's a handle that I can click and can drag up, and then that'll allow me to change the shape of these things. And you can do things like I can right click anywhere and say I want to put a picture or a diagram. So I say create picture here, and then I can change the type of picture. So they've got all these built-in images. So this is how you can add annotations as well to try to make, add causal loop elements to your diagrams. So anything else?
Is it easier to do it on Insight or Vim?
It's kind of up to you. I provide it because I think that students are bimodal in their preferences. I think some students really like Insight Maker over VinSim, but then whenever I go directly to Insight Maker, not only are the causal loop diagrams a little harder to make, but I find other students just really, like VinSim. So it's up to you. You kind of have to figure out which. If you're really working well with VinSim, I just stick with VinSim. Don't worry about it. VinSim is also sort of a well-known industrial tool that you find that a lot of companies are using. Insight Maker they could use, but it's often viewed as more of an educational tool. All right. Okay, well let's move on to today's main topic then. So I will close that out. So today we're talking about sort of how Morecroft introduces us to these system dynamics models. And I think a little bit of a slide are going to be cut off here, but we just have to deal with that. So Morecroft introduces us to stocks and flows. Same sort of stuff we already had talked about. So stocks, those are the big square things in the middle. They're the dynamic variables. They're levels. They're the things that change over time. And flows are the lines that represent how these stocks change over time. Flows make stocks change over time. Flows are the change in stocks over time. And so the idea here is whenever we draw something like this, so here's a simple model of a university that Morecroft used, and there's a stock of instructors, the number of faculty employed at a university. If this black bar was all the way up to the top, it'd be full. That'd be like the university is full of faculty. If it was down here, then there'd be almost no faculty at the university. So it's depicted here in the middle as their sort of half capacity. And we say the steady state value of instructors at a university is a product of how much faculty recruitment you have. We're doing a lot of hiring this week actually, and then how much turnover you have, so how many faculty leave. So this is like the birth rate and the death rate, and they balance out, and that's your steady state level here. Every time you have a stock, you have to give an initial condition. You have to say how many did you start with. So that's written in Morecroft's formulas underneath the stocks as this, whatever the stock name is, 0. This means the stock value at time 0. That's a parameter. You set that. That's up to you. And then inside VinSim or Insight Maker, it implements this formula, which we did inside Excel, but now we don't have to worry about that formula anymore. But that formula basically takes the number of instructors at the previous simulation step and adds to it whatever the net flow is, so the amount coming in minus the amount going out, times this little dt time step. And that little dt time step is something that isn't part of the model. It's not how we think of a university. There's nothing dt-esque about a university, but it's how we simulate a university is we have to come up with a dt to make this work. And so we take that formula and we could rewrite it just by moving these instructors over. So now we've got the change in the instructors is equal to the inflow minus the outflow times dt. And then if we divide by dt, then this starts looking like the thing that maybe you've seen back in calculus class. This is the kind of secant definition of a derivative. And so if I make my dt really, really small, then this thing starts acting like the derivative of the instructor's function. So creating a simulation model with a tiny dt with this inflow-outflow combination will give me the same rough shape of instructors over time as creating a calculus-based model down here where the derivative is equal to this recruitment minus turnover. So it's almost like we're just getting rid of the calculus and we're building the same dynamics a slightly different way. And so when we build this simulation up here, starting from time 0, and then doing this arithmetic over every step, step by step by step by step, we should get out, if we've done this correctly and if we're small enough dt, an instructor's shape that is equivalent to what we get if we solve this calculus problem down here, which is you take the initial number of instructors and you add on this integral from time 0 to time t of whatever our formula for the net flow is. And that net flow is that derivative. So we're just looking for an alternative way to do this without having to worry about the formal calculus. And that's what these tools allow us to do. And so when we draw this, like Morecroft did, what we're actually doing is creating a little derivative. So this right here is a graphical way to write this expression. So whenever you draw a stock, you basically take that stock and put a little DDT in front of it, and then take whatever sum of the inflows are, and they show up here, and then you subtract off the sum of all the outflows, and they show up here. And so this is the equivalently could be written this way, which means with our calculus, would end up being written this way, but we don't have to go this step. We can stop here and let the computer do the rest. So this is what the computer's doing, is it's effectively integrating under this flow formula. So to see what I mean by that, you could say, well, what does the instructor's formula look like when the net flow is constant over time? So saying that mathematically, what if I started with 0 instructors and I took the integral of a constant? What is the integral of a constant? So if I take the integral of 5 from 0 to t, then what is the answer out here? Does anybody sort of think that off the top of their head? What they would put here is the answer to that? So the integral of a constant. So I take an integral of 5, what do I get out? Yeah. That's the derivative of constant. So think the other way around, the integral, 5, or in this case 5t. Right, so I get 5t out. So my claim is that if I were to simulate this where I had a constant recruitment in and a constant turnover out, and the difference between them is that the recruitment in was 5 more than the turnover out, then I should get a rising number of faculty where they start at 0, but then they climb over time with a slope of 5. And that is what the simulation shows us. Is it so in Morecroft's case, he's got, remember this, the way these graphs work, we look up at the legend, 1 instructor, so we look at the line that has a 1 in it, this is the instructor line. 2 is recruitment, it's at 5, and 3 is turnover, it's down here at 0. So there's 5, the difference between 2 and 3 is 5, and so this 5, I'm basically just taking the area underneath this curve as I march along here, and that's what gives me the rising instructors over time. So the simulation gives me that out, but so does the math. If I were to solve the math, and plot this 5t, I would get exactly this line. But I don't need to do this anymore because I can just give the derivative, give this basically diagram to the computer, and the computer, well, as long as it's a small enough time step, will end up simulating this line, and it should fall right along the same line I get if I were to solve the math myself. So that's what we're doing. So I can then expand that and say, well, let's test different what-if scenarios that might be a real pain to do if I were to do it the calculus way. And so I can flip my world up here into 4 different regions. I can imagine a region of growth, or where my recruitment is higher than my turnover. But then you can imagine over time, there might be a point where your turnover starts to rise and your recruitment stays the same, where then that turnover becomes larger than the recruitment. And then the turnover flattens out. And then the simulation would suggest that we would get a curve like this. And so we can look at those 4 different regions, and when I have my constant net inflow, not surprisingly, I get a line out of here. When you integrate under a constant, you get a line. And then in the second region that the simulation has for us, I see that the net inflow gets smaller and smaller over time. And so not surprisingly, what was a line becomes a curve that flattens out, and it becomes a 0 slope, so it becomes horizontal, the slope here, exactly where these two, the net inflow goes to 0. And then when the net inflow becomes negative, when the turnover is greater than recruitment, then it curves back down the other way. And then finally, when I get a net outflow, so you can think of it as the net flow is negative because 2 minus 3 is negative, then I get a straight line coming down the other way. So this arc that would have required me to solve 4 different integration problems and string them together, inside Insight Maker or VinSim, I just have to set up my recruitment and turnover to have this pattern, and I hit go, and then the output I get ends up having this same shape here. So I am solving a calculus problem without having to do the calculus, and it allows me to put in potentially exotic functions in for this net flow formula and take the integral under them without ever having to actually take the integral. That's kind of what we're doing here. To think about it in a different way, you can imagine, so I'm just walking through the 4 phases here. To think about it in a slightly different way, you could imagine what would Isaac Newton have done if he had computers when he was coming up with trying to understand what happens when you throw an apple into the air. So I throw an apple into the air, and so I'm interested, I give the apple some initial velocity, and I watch its position over time. We know that the apple rises over time, we know that it falls eventually, we know it eventually hits the ground. Newton said, well, what is causing the apple's velocity to change? And the apple, and so he was saying, well, there's this gravity thing, and I'm going to say that the change in velocity is just equal to the negative of whatever this gravity thing is. You guys okay over there? Is there an issue?
She's good, yeah.
So if Newton had a computer, instead of coming up with calculus, could have maybe written it like this and said, I have a changing variable over time, velocity. And what's causing it to change over time? It's my acceleration due to gravity. So this is another way to write this expression up here. And then I said, well, how does velocity relate to the position over time? Well, position, Newton said, well, without the computer, he said, I need a formal way to model this. Velocity is just the change in position over time. So he wrote this second differential equation. Now we could draw another, diagrammatically the exact same thing where you say, all right, well, the velocity, that's just the flow into the height. And so we can draw height as a stock with a flow and velocity as a stock with a flow, connect all these things together, and we have written exactly the same thing that Newton did when he sort of wanted to describe what happens when this apple gets thrown up and then comes back down. And so for Newton, he didn't have the computer to integrate through and do the tedious task of what we did in Excel. And so instead, he had to come up with a formal way to solve this expression. And so you might recognize some of this expression here from, from a physics class or maybe even from calculus. And so it's possible to take this and turn it into this expression where you've got an initial position of the apple, an initial velocity of the apple, and then you can predict this curve over time. But it turns out that if we wire this thing up the same way and hit go on VinSim, we get a position curve that looks like this, and a velocity curve starts high and goes down and looks like this. And so we get the exact same story out. And so it's an interesting thought problem to think about if these kind of integration methods were somehow available in the time at which Newton and Leibniz were coming up with calculus, would they have even come up with calculus? Because you could just put it into a spreadsheet. You could have put it into VinSim, and this is just as interesting. You say, well, now you've explained to me that gravity is driving this arc of the apple. You've convinced me with this plot. This plot is just as convincing as that expression. So why do we even need that expression if I have this plot? So you can view these tools as alternatives to the formal methods you would otherwise do in calculus. And a big reason why we still have those formal methods is once upon a time, computational methods were actually not as cheap as they are. But now, we've got, every computer in front of you has got the power to do this that wasn't available when Newton was developing this, so this was all that they had available. So that's the motivation behind these stock and flow models. Are there any questions about any of that? Yeah.
So in the chapter meeting, they excluded, or they just put all variables like students, faculty, and instructors as just instructors. Are we supposed to keep it more simple?
That's a good question. So they're saying that in the chapter reading, they created the sort of a single stock that represented a lot of things. It just depends on how much detail you're trying to explain in your research question. So if I'm just interested in the population on campus, then why model all of them if they're all going to end up being affected by the same things? Just group them all together. But if I'm interested in how the number of, say, good quality instructors affects the number of students, then I might need to keep an independent count of those because they might not be in phase with each other. All right, good question. Any other questions about this basic mission here, how, where we're going into the modeling of this and how we're sort of getting rid of the calculus as an alternative to these formal methods? Okay. All right, so where do we go from there? So so Morecroft gives us some hints that for how we build these models. And his first hint is the different types of stocks that you look for in these models. And he has these two groups, tangible stocks, which in this model were they like staff, studios, correspondence, transmitters. Can somebody define what is a tangible stock? Why is it tangible? Brandy. Oh, Will, sorry.
It's something that you can actually turn, like in this example,
Language and program quality. Right, good, excellent. So right, so the tangibles are things that in principle you can pick up, they exist physically, they are countable. They are easy to number, they're easy to count, it's hard to argue they don't exist. You have a number of staff, you have studios, you have correspondents, you have transmitters. But then he has these intangible ones like program quality. Well, it's hard to measure program quality. It's subjective. It doesn't exist. You can't put it on a shelf. Likewise, languages. Now, you can count the number of languages that are represented, say, among your correspondence or among your programs, but it's still not a physical thing that it would take sort of a second order inventory where you almost have to look at through all of your programs first, and then from them look through and see which ones are in English, which ones are in Spanish, and so on and so forth. And so they're intangible, but it claims that we need both. So why should we bother modeling something that doesn't have a physical reality? What's Morecroft's argument? Why do we care about these softer, intangible stocks? Why not just stick to the tangible stocks, the apples and grounding? Yeah.
Because they affect the tangible stocks and they affect the number of listeners.
Excellent. The answer there was they affect the tangible stocks and they affect the number of listeners. They matter. So we can't get away with excluding these because they ultimately have a effect on all of these things. We don't understand the dynamics of how we get more correspondence and more transmitters without understanding our program quality. So even though these aren't easy things for us to count, we still need them because somehow they play a part in the dynamics of it. So we might have to invent intangible stocks that we will have to make an argument that they actually exist. Someone might have said, program quality doesn't matter. And you might have to make an argument that this thing called program quality matters. And you might not even know what the true program quality is. You might have to make an argument that your model tells them they need to invest in studying program quality. And so your model would say, if we know about program quality, we could predict these things, but we don't know about it, but we think it's important, so you need to go out and study that. So coming up with these intangibles can still be important, but they can also be some of the more subjective and the more difficult things to see, because ultimately you look in your inventory and this is all you see is your tangible stocks. You have to really think about the system to see what the intangible stocks are. So these are the dynamic variables that are somehow hidden from physical reality but still affect the dynamics of the physical variables. So are there any questions about that, the difference between tangible and intangible? You'll certainly have both in the models that you build, say, for your final project. Okay. So once we have our stocks and our flows, then we need to link them all up together. And so these are these coordinating networks. So that was like the 2-word answer to that second question that I was looking for. But if you just said causal links or something like a network of links or something like that's fine too. But basically, if we just have, whenever I have a stock, it's implied that I have a flow. But if the flow doesn't have anything linked up to it, then it's not an interesting diagram. It's only interesting when I export and import information from other parts of the diagram, and that's what this coordinating network is all about. And so the idea being is I have that I can export B and C into this variable A, and this A will end up being a formula that combines B and C, and then A itself can be exported into something else. And so these links allow us to build formulas, and they are wired up from kind of the right-hand side to the left-hand side. So if you need something in the formula, you have to wire it up to the thing that the formula represents. So I need B to represent A, I need C to represent A, so I wire them up that way. And then that allows me to make A depend on the dynamics going on at B and C, and so on and so forth. So that's what we mean by a coordinating network. They tie the action of all these things together. Any questions about what I mean by coordinating networks or how to form these things, formulas? I want you to be able to stare at a formula and be able to draw a corresponding coordinating network. That's a feature that you can expect to hopefully acquire by the time of the midterm. Okay. All right. So the next thing is, we're gradually bubbling up into how we make our diagrams more interesting, more complex, more realistic. And so sector maps. Now I've put some other videos on Canvas. This gets more advanced, but if you're interested in how to build sectors that are actually sort of tucked away in convenient spots inside Vinsim and Insight Maker, I've got some tutorials online that I've put together about that, about folders, views, shadow variables, and ghost primitives. This is something that we'll get closer to as we get after the midterm, but just sort of a heads up that those things are there. So if I draw a causal loop diagram, I might be able to argue with someone that this is how, say, a crime spiral works in a major metropolitan area. But if I actually want to simulate it, this is probably not enough detail to actually put into a stock and flow diagram. And once I start adding in all of these intangible stocks and tangible stocks and coordinating networks, it becomes a really ugly and really big diagram. And so the thought is, maybe I can break this task up into sectors, and then I build models inside each one of these sectors. And so this is Morecroft's term sectors, and this is our sector map, how they connect together. And these connections are a little less formal than the connections here. So the idea here is I've got these 4 sectors here, and if I zoom in on each one of them, I maybe see this diagram inside the community sector, this diagram in police department, this diagram in street market, this diagram in the drug users. And notice I don't have any connections between the sectors, but I've colored them by variables that show up in different sectors. And so up here, call for police action shows up in the community sector, but then it also shows up in the police department sector. So there is informally a connection here. You could put all 4 of these together into one giant stock and flow diagram, but instead, for convenience, I've broken them up into 4 separate stock and flow diagrams. And that just makes it less distracting as I'm building these things. And so I can also, when I'm giving my narrative to my reader, it's easier for me to have them focus on just these set of variables, so they're not distracted by these. So I can zoom in and say, study this or this, and so on and so forth. So in your final project, for example, I'll get to your question in just a second, you could imagine, rather than showing a giant stock and flow diagram in your 4 pages that you're restricted to, you could say, we've got the full model in the appendix, but we are going to focus on where most of the dynamics happen, which is this sector. And then you just have me drill down into this sector. And if I'm interested in the other stuff, but the other stuff is kind of, it's more stock. It's something that is, maybe it's just a population model. It's nothing special. Then you could say, well, we've put that in the appendix, but the stuff that's unique to our system is in this particular sector, and so we're just going to focus on that. There's a question?
On the last slide,
yeah.
The CLB, why is there a plus between supply and price?
So it might be, so I remember that in this chapter, there was at least one of these that I had to fix in the PowerPoint by putting something above it, and that might have been that, because I would agree that this needs to be a minus to make this a reinforcing loop, and just to be, as supply increases, price decreases. So I think that's a typo in Morecroft, that when I showed this in an earlier lecture as an example of a CLD, I think I hid a little minus over top of that, but I forgot to do that in this one. But good call, that's definitely should be a minus there. As supply increases, price should decrease, and vice versa. And with 2 minuses, then this gets reinforcing. All right. Okay, so if I just zoom in on police department, for example, and I would say, how do I build one of these little sectors? How do I build the formulas in this? Maybe the diagram makes sense, but then how do I actually come up with the math, the arithmetic inside the formulas? So if we look at this, we're saying, okay, we've got, I drilled down here just into the stock and the immediate flow going into that stock. And I see this is the number of police allocated to drug busting. And I put the units out here, police officers. And then down here, the rate, change in allocation of police officers per month. So time to move staffs, months, indicated allocation of police officers. And so putting the units up there can be useful because it helps us understand how formulas might come together and what formulas are totally illegal. So as an example, I know that the update formula for the stock here that's implemented inside VinSim is going to be the number of police officers last month plus DT, which is in terms of months, times the change in allocation of police officers. So you say, well, how do I get from police officers per month to police officers? Well, that DT is in terms of months. So when I multiply the flow by the time, that turns the flow into the stock units. So suddenly it makes sense. Now I can then say, well, how do I build this flow formula? Well, so then I can say, well, let's look at the things wired up to it here. So I need something that on the left-hand side is police officers per month. So I need to figure out how to build a formula based on these things that gives me police officers per month. Now there might be lots of ways to build that formula, but more often than not, there's more ways that don't work than ways that do work. So it provides you a method for restricting the search of the different formulas that are available. So here I think things through and I say, well, I need to build a formula that's police officers per month. Well, let's look up at police officers and think about these things through. Well, I've got the number of current police officers available. I've got the number of police officers that have been indicated as needed, say from City Hall. And so those are both coming in. So let me just take a subtraction of those because the units here match. So I'll subtract that and I get a difference in police officers. So this is how many police officers I need over and above how many are already there. So I've got that right there. That's police officers, great. Then what's the other thing? Well, I can't get police officers for free immediately. They have to go through training. So for every one police officer, it's going to take time to move staff, months, in order to bring that police officer onto the street. So I can put that thing up there. So time to move staff. So I've got that going in here as well. And so now I can say, all right, well, for every one police officer, it's going to take them this much time. I can put that I can phrase that a different way, where I can say every tiny unit of time, this much police officer will go onto the street. So this is kind of like we're taking that averaging approximation we did with the bacteria. We know we actually have to wait, say, 6 months to train a police officer. But we're going to simulate day by day by day. And if I simulate day by day by day, then this is a tiny little fraction of police officer that goes onto the street, so that after 6 months, I get a full police officer. So that is my per police officer rate, and this is at least starting to look like it's in the correct units. So then I multiply that by the total number I need, and now I have got a rate, at least something that is in the right units of police officers per unit time, per months. Police officers per month, and that is my formula for flow. So that provides me a feedback, a balancing feedback, where City Hall asks for a certain number of police officers, and after a delay, the number of police officers on the street rises up to that level, just like the water level in the back of the toilet tank. This is effectively the same formula that you implement when you build that toilet tank model, either in Excel or in VinSim. So any questions about how we formed those formulas there, or where this formula comes from? Does this formula make a little bit of sense? The number, so I just have these three things coming in. The number of, this is my target water level, this is my current water level, and this is that time constant. This is roughly the amount of time the water takes to hit 63% of its total, or another way, this is a sort of the amount of time it takes a police officer to get to, say, 63% of through its education. So it is a method of sort of slowing down the system that we have to deal with. Okay? All right, so that's how we set the flow. So then let's look at a different formula here. drug seizures down here. So I've got number of police allocated to drug busting. That's that stock that we just handled the flow in here. And then I've got police effectiveness in drug busting. I've got this as a constant, and its units are kilograms per officer per month. So every officer takes this much drugs off per month. So it's kind of a mouthful there. And I've got here police officers, not police officers per month, police officers. So I've got police officers coming in, and I've got kilograms per officer per month coming in, and I want inside here this to just be kilograms per month. So immediately I look at that, and there's not a whole lot of ways to take a variable with police officers as a unit and a variable of kilograms for police officer per month per unit, and then get a unit of kilograms per month out. And the way in which I do that, so I look at these things and I say, all right, I want this out. This is on the left-hand side. I want these to be on the right-hand side. Well, if I look at that, if I could just cancel police officer here, I get my kilogram per month. And I do that just with a multiplication. So I can say the drug seizures are just the police effectiveness times the number of police. And that formula, not only does it make sense in terms of units, it just makes sense. I'm saying that every individual officer can take this many drugs off per month. And so I'm multiplying by the number of police officers, and this tells me how much the entire police force can take off per month. And all the units end up working out. So any questions about that, how we form that formula? So this is the limit of math for these types of models. We are going to build relatively simple arithmetic. If the expressions you're building are getting too complex, that probably means you should move the expressions out into a more complex coordinating network so that your network has a bunch of nodes that are simpler. And effectively, the complexity of the math gets pushed up into the complexity of the visual network instead. All right, questions about any of that? Again, there are tutorials on how to do these views and folders that makes this sectors even nicer, but we don't get into that till after the midterm. All right, so then we said we've got the model built, and now we want to use the model, and we want to do what's called verification and validation. So we want to be able to see, is our model operating correctly? So that's checking for bugs, that's verification. And then we also want to do what's called validation, where we say, does our mental model actually match what we think is going on in reality? And so when I end up running the model, it runs and it looks roughly qualitatively like what I was expecting. So supply of drugs starts high and it gets low. So initially, it seems to at least pass the verification test. I think I built the model correctly. I don't think I switched any signs. I think all my expressions, there's no, I didn't multiply something when I meant to add it or vice versa. But validation, and say this starts looking unrealistic towards this end. And there are two problems that Morecroft points out. One of them is that if I look at the supply of drugs, so that's the second, so because notice the legend, 1, 2, 3, all the way up to 5, I have to look at the second number here. And so that tells me that supply of drugs on this axis, this is the 0 line. So the supply of drugs, this number 2 line here, it hits 0, and then it goes negative. So what does that mean for the supply of drugs to be negative? It's that just doesn't make sense. They've taken all the drugs off the street, and somehow it's almost like the police are manufacturing drugs in the lockup somehow. So that doesn't make sense. And then the other thing is when these drugs go negative, then we see that, so it's can't see it because the projector, but the price gets unrealistically high. And in some ways it makes sense because the drugs are going so negative that if the supply is negative, then maybe, the price should shoot up to infinity. But we know that realistically, you would never have drugs that would be that expensive, because once drugs were that expensive, regardless of how effective the police are, people would come just from everywhere to sell drugs. I'd be selling drugs, because why would I teach if even at high risk, it would be this high? So this just does not match our model of reality. It passes the validation test. So that indicates that we have left something out. So this isn't just a mere software bug. This isn't just an algebra problem. We have left something critical out. And so we need to think about what variables do we need to put in to make this more realistic. So let's focus on assumptions that we made that might have been wrong. So one assumption is that police are equally effective at finding drugs regardless of how many drugs are available. That is probably unrealistic. As there get fewer and fewer drugs, they probably become harder to find. And so, but because we assume police are equally effective, even when there are 0 drugs, we're modeling the police as finding drugs. When there are 0 drugs, the police better not find any drugs. So we need to update this so that that's not a problem. So the solution, let's make drugs harder to find at low abundances. And if drugs are infinitely elusive at low abundances, then the stock will never go into the negative because the police will just stop finding drugs. So that makes sense. So how do I implement that? Well, I can implement that by connecting, and this isn't done in the book, but it just said you could do this. You can connect the drug supply to police effectiveness. This right here is modeled as an exogenous input that it's not, we want to make it endogenous. So we want to basically say, take the number of the drug supply and have it determine the police effectiveness. So if the drug supply is wired in, we can make police effectiveness dynamic and have it change over time. It might start at a particular level, but as the drugs go down, so will the police effectiveness. And that will end up being a feedback that prevents this from ever going negative, or prevents the number of drugs from ever going negative. So that's what we're kind of, these are options that we're saying here. So that makes sense for this first problem. We're going to solve the first problem by making police effectiveness decline as the drug supply declines. We're going to make it harder to find drugs as drugs become less available. Makes sense, right? Okay, so the other problem we have is that we say, well, the total supply of drugs is constant. And so if the total supply of drugs is constant, so there's a fixed amount of drugs per month, once you take all of the drugs off of the street in a city, they become infinitely elusive, and the price for any little bit that might be left over is going to skyrocket. So the supply on drugs can crash to 0, causing street price to grow without bounds. But like I was saying before, in reality, if the price signal starts going high enough, then it's going to encourage others to move into the market, and you're going to get a supply of drugs, so the drug supply will be reinvigorated by others providing that supply. So we need to allow the total supply of drugs to respond to price signals, and so we need to model the injection of new drugs or suppliers when you get the prices being high. How do we do that? We can add to our model a new flow and coordinated network linking street price to total supply of drugs. So here we got total supply of drugs coming in, we've got street price up here. What if this total supply of drugs has its own inflow, and that inflow is affected by street price? That would allow the supply of drugs, if the street price gets high, to then suddenly increase, and then that would create feedbacks on the street price. So now you would get a feedback between price and the supply of drugs that might cause things to level out. And you could then start predicting realistically what level are things going to settle out at. I will constantly be pulling drugs off the street and putting them into police lockup, but I will keep the total supply of drugs on the street relatively low, although the street price will be relatively high. If I'm okay with there being a high street price for drugs and always encouragement for people to bring their drugs in, so long as the level stays low, then maybe I'm okay with that and I keep my policing up. Or you might say, you know what? I don't like that. I would rather not police, and then maybe suppliers will bring their business elsewhere, and the total supply of drugs might actually might rise a little bit, but it'll stay low, and then I don't have to constantly be taking drugs off the street. So you could play with those different scenarios with this type of model. So any questions about that? Yeah.
Could you please re-explain changing the variable from exogenous to endogenous?
Oh yeah. So all.
But in different words.
Sure. So when I was saying, maybe the previous one, this one here, so when I said that this is an exogenous variable, what I mean by that is that its value is set external to the model. You, as a designer, just choose a number for police effectiveness. You look it up, you Google it. So Google is not, the dynamics of Google, which I just triggered Google, does not factor into the model. Making it endogenous means that I'm going to make this value depend not on what's on the internet, it's going to depend on the rest of the model. So by closing that loop, I internalize or make, it's transcribing all of that, I internalize or make the whole, this whole process part of it. I still have to set maybe an initial condition, but I then allow this thing to fluctuate in a way that doesn't require me to just set it ahead of time. So endogenous just means set from the outside world. You have to look it up in order to put it into your model. That's exogenous. Endogenous means determined by inside the model. Does that make sense? Yeah.
What kind of equation would you use? Sorry. What kind of equation would you use to incorporate the drug supply into police effectiveness?
Sure, so that's a good question. This, coming up with these equations, there's some subjectivity, and you would ultimately have to do another study in order to figure out the right form of these things. And usually exactly the right form doesn't matter, just so long as it has the right shape. And so you can do what's called a sensitivity analysis to say, I tried a bunch of these different functions, but all the ones that had this shape seem to match what we found in reality. So for example, if I called drug effectiveness E, and I called drug supply, which, let's say drug supply, which is I think not on here, if I call that S, then I might create a formula like I want to say effectiveness is equal to, I don't know, I could say some baseline level of effectiveness, which maybe I'll just write as capital E, times maybe 1 minus the drug supply divided by, I don't know, so coming up with this on the fly here and then making sure I didn't flip my logic. I might need to flip this thing around, but the idea is you come up with a sort of a formula like this one where in this particular case as the drug supply became high, then the effectiveness would go low. So I need to sort of flip that. And so if you imagine, what if I did, instead of S over K, like K over S here. So if K is like some constant that I set, like whenever the drug supply, so if I don't want that because it's, so let's notch out all of this. So what I want to do is I want a formula so that its shape should look like this. As the supply gets large, as the supply gets low, the effectiveness is low. So I basically want something that maybe looks like this. So if the supply is, just screwing up all of it. So sometimes the projector, for some reason, initializes, like, so the top is, so what I'm trying to draw here is a function that, and it's always easier for me to draw these things out, that looks a little bit like this. So that if supply is very large, the effectiveness is maxed out. But as supply gets lower, it pinches effectiveness down to 0. And so there are a bunch of functions that look like this kind of S-shaped function. So I'm kind of looking for something like supply divided by supply plus some constant I'll call C, and that whole thing times E. And so a function like that is supply becomes infinite, then this whole function just becomes E. But if supply is 0, then it becomes like E over C. So it allows me to sort of say, well, the effectiveness is going to scale from E over C up to E as long as I have, as my supply goes back and forth. So it was a little bit of a train wreck, but I hope that makes sense. Okay. All right. So wrapping up here. So we, questions there. All right. So yeah, any other questions? Okay, so moving forward, so this is lecture D4, so we've got the midterm coming up, and so then we'll start lecture Unit E. So your next chapter that's due is not due until the end of Unit E, so it's for quite a while here. So, but reading through chapters 4, so you're going to, the next chapter will be chapter 6. Chapter 5, if you want to read through it, may actually be some useful help when studying for this midterm. It goes over some concepts that might help solidify things that will show up on the midterm. Start forming your teams. The teams should be formed by the Saturday. Basically, this is the Saturday after spring break. So lecture E1 will be right before spring break. I say Saturday after, but you can insert spring break in there. I think on Canvas, it's actually due the Saturday that is like just before you come back. So insert spring break between, so E1 spring break, and then I need to know who's on your teams. Then that week, I will create your groups on Canvas. And then roughly a week after that, you write this short one-page document or so telling me roughly what system you're planning on modeling. I know you're not going to know what the stock and flow model looks like or any of that, but say we're interested in modeling this system, and here are the dynamic variables that we think are important, and so on. And that's in that document, that information page that I have on Canvas. So then the assignments that are due, and then shorter term, there's a Muddy's Point this weekend, and then that assignment D3, which is just the VinSim model of the toilet model. Midterm's coming up, and so basically the next lecture we're going to have a midterm review. Then we have this in-class midterm, and then we'll have a retake. So basically you can think Tuesday we'll have a review, Thursday a midterm on Scantron. Then the next Tuesday we'll have the retake, and which you don't have to take. In fact, you don't have to take the first midterm if you want to only take the retake. That's fine too. And then we'll have lecture E1, which will be the Thursday before spring break. And then spring break, and then that's everything moving forward. So, any questions? Well, I'll put that up while I'm, yeah.
Will there be anything like a study guide or anything like that?
All that, if you go to the midterm module on Canvas, I've got all that study information there. Yeah.
How many people can be on the team?
4 people per team. In fact, I think I want it to be 4 to keep, we have about 30 people in the class, and so it makes it a little manageable. So, unless there's a special circumstance, 4 people. Anything else? Okay, so for attendance question today, let's say, so what term did Morecroft use to represent the network of links that tie everything together in a stock and flow model? So this was also an answer to one of the questions on the assessment. So what is the term, a 2-word term that Morecroft uses to represent how all the links come together in a stock and flow diagram?